So this is what we did yesterday. Again, we had 6 arrangements for the letters in TOP. The reason I want to look at that is because today we're going to start with something similar, but now we're going to look at how many permutations are there of the letters TOO. So again, we're imagining the T and the O are all on Scrabble tiles. How many different ways can we arrange them so we can actually tell them apart? Could you write out the options? Okay, let's go over these questions. Number 1, you got these 3 options, yes? Good, we'll come back and talk about that in a little bit. Number 2, anybody get 12? 11? 10? Ooh, lots of 10s. So, here are the ones that I came up with. So why would we have that restriction that we always have to move right or down? So we can't go left and up, but why? Yeah, but what if I want to backtrack? Pardon me? It'd be counterproductive. How many possibilities could I come up with? Oh, it's still going to be just this big. Yeah. Yeah. So it would be kind of a pointless question if I could kind of loop here for a while, and then I'm going to go there, and then I'm going to loop here, and then I'm going to come back and go there, and then eventually I'm going to come here. There's one possibility. And because you could loop infinitely, yeah, we'd end up with infinite possibilities. So it would be not mathematically useful at all. So we put in that restriction that we always have to be moving closer, which generally, if you think of maps and paths and that sort of thing, even in electronics, kind of if you think of a circuit board, there's a pathway to get from somewhere to somewhere else, right? So you're thinking about pathways for that sort of thing, and you want how many pathways you can get. So we come up with 10 for that. So what happened in this question is for all of these, I had some similar movements happening. As in for this one, I go right and right and right and down and down. And for my next one, I go right and down and right and down. And then if I pick some other one, I go right and down and right and down and right. What's the same for all of those? Yeah? Yeah, not only the ratio, but the exact number. I have to go right 3 times. I have to go down 3 times. 2 times, yes. So, as we look down here, question number 4 is worded differently, but really it's the exact same question. Right? Because I have 2 D's and 3 R's that I need to rearrange. It's kind of like going down twice, going right 3 times. And I'm just arranging the different orders that I can move them. And so for all of these, kind of the first one, I had 3 R's to begin with, then 2 D's. For the next one, I had 2 R's, then a D, then 1 R, then a D. So I'm just looking at the rearrangements of those letters. So let's think of it with this question down here. If I'm arranging 5 things, typically we'd think I have 5 factorial ways that I can arrange them. But because some of these look exactly the same, the 2 D's I can't tell apart, the 3 R's I can't tell apart. Now, up here in the diagram, I could tell them apart visually, but in terms of summarizing with rights and downs, there's no difference to them. So I imagine I'm arranging all 5 of these, but what am I not arranging? Well, there are 2 D's that I can't tell apart. So remember yesterday we said and meant multiply, and not means divide. So I have 5 things I'm arranging, but I'm not arranging 2 D's because I can't tell it apart. If I switch the 2 D's here, it looks exactly the same. And I'm also not arranging the 3 R's. Guess what this equals? 10. So we call this a permutation with repetitions. So it's different, again, than those first questions we did where we had 3-digit numbers, where we could reuse the numbers. But what we're saying is we have some objects that look identical. So we could say it's permutations with identical objects that we can't distinguish. And so we have fewer arrangements because the identical things, we can't tell them apart. So in general, the number of permutations on n objects would be n factorial, but if a of them are alike, kind of like down here, 2 of the d's were alike, I'm going to put an a factorial, because a would represent how many of object 1 look exactly the same. And if b are alike, then I'll have a b factorial. And that's like saying I had the 3 r's down here, and so I divided out the 3 factorial, and for however many things are alike, I just keep multiplying things in the denominator. Because I'm not arranging those objects that look identical once things have been placed. Karina. So if we did 5 factorial over 3 factorial, then I'd get 5 times 4, but then I still need to divide by 2, which will give me the 10. So let's expand this out. So the 3 factorials would cancel out, but then this 2 goes into 4 twice, and we do end up with a 10. Yes. Theoretically, yeah, there could be an infinite number of things alike. It's just not practical for actually calculating. So here we have some things alike. And look at this. This is already the last page of the lesson. How many ways can we arrange the letters in the word monotonous? So I'll give you some time to work through this page, and occasionally I'll interrupt and go over one of the questions. Number 6 and 7, the numbers in the question are the same, but what it's describing is slightly different. So I drew it out. So for question number 6, she's going 9 blocks. She always goes 5 blocks west. So from her home, she's going to go west 1, 2, 3, 4, 5 times. And she's going to go north 4 times, 1, 2, 3, 4. So what I'm told in this question is essentially I'm told obstacles, right? So I'm told the blocks. She has to stay on the streets. So the numbers that are showing up here are the numbers that are in my calculation. So the 9, the 5, the 4, not too bad. But the next one, I'm not told obstacles, I'm told pathways. And so that's why my result is different. So here, I have 5 avenues running east-west, so I have the 1, 2, 3, 4, 5 horizontal lines. 4 streets running north-south, 1, 2, 3, 4. I didn't space them evenly just because they don't have to be. So we generally assume they are, but they wouldn't have to be, and we'd still get the same result. similar in that we're starting in the southeast or the bottom right, and we're heading to the top left. But now the number of stages I'm going through is smaller because I only go west 3 times, I go north 4 times, so the numbers that showed up in the question aren't the numbers that show up in my calculation. So I need to be careful that I'm thinking about what's being described. Are they the obstacles? Are they the pathways? When in doubt, just always sketch a diagram. And I'll let you work out the actual numerical answer, but these are the calculations we do. So those two would be different results. Questions? Yes, Nathaniel. Let's see. Are you talking about number 7? I have only 4 streets running north-south, which means I have only 3 blocks, right? So I have my 4 streets, my 1, 2, 3, 4, which means I'm going west 1, 2, 3 times. Other questions? Nope. Let's look at the last one. 12 pieces of trail mix left in a dish, 5 almonds, 4 dried bananas, 3 papaya chunks, and Corey eats the trail mix one at a time. How many ways can he eat the trail mix? Now there's an assumption in this question that perhaps should have been stated, which would be the 5 almonds we can't tell apart. Now maybe there are distinctions in almonds that your decisive eye could determine, but for the purposes of this question, we'll assume that they all look the same. So probably could have been worded better. So if I have these 5 identical objects and then 4 identical and 3 identical, then in total we have 12. 5 of them are the same, so I'm not going to arrange those 5. Whether I eat almond 1 first or almond 2 first, we're imagining it's essentially the same thing. 4 factorial and 3 factorial. Any questions with 8? Nope. So we should do 1 diploma released question. 1? Yeah, 1. So hopefully everybody found this an easy question. Is your answer bigger than 59? Yes. Is it smaller than 61? Okay, so I'll leave that up to you. Oh, yes, you nailed it.